Now it's my pleasure to introduce Wojciech Domitrz from Warsaw University of Technology. We will talk about singularities of Gauss mapping components of surfaces in R4 and holomorphic curves. Thank you very much, Wojciech, for accepting the invitation. You can start when you are ready.
I'm ready. Okay, thank you very much. Thank you very much for the opportunity to speak here on this nice webinar. And I will speak about singularities of Gauss map components of surface in R4 and holomorphic curves. This is joint work with Yvonne Hernandez-Martinez and Federico Sanchez-Bringas from Mexico. Unfortunately, this is not a talk with a Brazilian mathematician, which I have a very nice cooperation, but it is motivated by the questions that I have after my talk on the last conference in San Carlos, on the last workshop, international workshop of real and complex singularities. After my talk on the first part of this subject, of this part, I have a lot of questions, and this talk is just the answer to these questions. So I will, if somebody was on my talk in San Carlos, I will repeat the beginning to recall the things, the subject. Okay, so I will study the Gauss map of M. M is a smooth oriented surface, and and this map is an immersion, yes, to R4. Yes, so the Gauss map maps, this is the map that maps any point to the tangent space, which is a subspace of R4. So this map, the Gauss map, goes from M to the oriented Grassmanian, because our surface is oriented Grassmanian, Grassmanian of oriented two-dimensional subspace in R4. So first, I will explain the structure of the Grassmanian, of oriented two-dimensional subspaces of R4. Okay, sorry, not this way. Okay, so the subject of this Gauss map was first studied by Wilhelm Blaschke in the late 40s, and then by his PhD student, Hern and Spanier. They wrote a paper. In this paper, they explained in a very easily way the structure of the Grassmanian of oriented two-dimensional oriented subspaces of R4. Okay, so I will use this explanation. Okay, so we have this Grassmanian, yes, and we just take a positive orthonormal basis for R4, yes, E1, E2, E3, E4. And V is an oriented two-dimensional subspace. We will use the Plicker coordinates of Grassmanian, of this Grassmanian. So we take just V1, V2, a positive orthonormal basis of V, and we take the wedge product by vector V1, wedge V2. And we can, of course, write it in a base of the bivectors on R4. The base we take, which is E1, E2, E2, E3, E3, E1, and so on. And these are the coordinates in this base. But it's not true that any bivector just determines oriented two-dimensional subspace. They have to satisfy these two equalities, yes, because first it must be the bivector which is of the form of the wedge product of two vectors, yes, and the second of all, we must remember that this is positive orthonormal basis of V, so they are orthogonal and they are of the norm 1, yes. So if you have, the coefficients have to satisfy these two equations, yes, these two equations. Okay, sorry, not this direction. But if you change, if you take another orthonormal basis of the vectors on R4, Yes, why I can say orthonormal? Because using just the determinant, you can extend the scalar product on R4 to the bivectors. You just take the determinant of the vectors which are in these bivectors. And when this x1 given as a 1 over square root of 2, e1, e2 plus e3 and 4, and so on, y1, y2, y3, x2, x3. This is another orthonormal basis of bivectors of R4. And then if you use this basis, x1, x2, x3, y1, y2, y3, instead of the previous one, then v1, v2 can be written in this way, using this basis xi, yy, and then the coefficients beta I, gamma I, have to satisfy this equation instead of this previous one, which were satisfied by alpha ij. And when you see that the structure from these two, you see this is thus the equation for a two-dimensional sphere in R3, and this is the equation for two-dimensional sphere of R3 of the radius 1 over square root of 2. So the Grassmanian of oriented two planes in R4 have a structure of the product of two spheres of the radius 1 over square root of 2. And this is important for our consideration. Okay, sorry, not this way. Okay, so we have, in fact, the Gauss map have two components. These components are given by the projection by the composition of the Grassmanian, yes, by the composition of the Gauss map with the projection of this product to components, the first one and the second one. So the first component we call G1 and the second G2. Gi is given by the composition of the Gauss map with Pi, the projection, the natural projection. Okay. And then if now we will change notation. Now E1, E2, E3, E4 will be a local Darboux frame on U. So what it means? That this is a positive orthonormal frame at each point of our surface, such that for any point of our surface, the first two vectors is just a positive basis of the tangent space of M at the point P. Yes? And we use this E1, E2, E3, E4, yes, as in previous way to describe X1 and Y1, which will be also vectors. We have a frame X1, X2, Y1, X2, Y2, X3, Y3, using the previous formula, but now at each point, E1, E2, E3, E4 is a local Darboux frame. When G1, when G, the Gauss map, in this using this local Darboux frame, has the form E1, UH, E2, and G1 restricted to U, yes, is just 1 over square root of X1. When X1 is given by the previous formula, but now E1, E2 is not orthonormal basis, but orthonormal frame, yes? And the same with G2, restricted to U, is a 1 over square root of 2 Y1. When X1, Y1 are given in the previous formula, but the meaning is the following, that instead of orthonormal basis, we have orthonormal Darboux frame. Okay. Sorry, not this way. Okay, so I will call some notation and some classical formulas. So X denotes the immersion, this immersion of the surface into R4, yes. And then if we take dx, and then dx can be described as θ1 E1, θ2 E2, where θ1 is just the scalar product of dx and I, yes. Theta I is the dual basis of the dual space of the tangent space, yes. And of course we can take dEI, and when we obtained omega ij, this is the elements of the connection matrix, yes, EI, and of course we have this formula for omega ij. Of course, theta 3, theta 4 are 0, yes, since E3, E4 are orthogonal, they do not appear here, so it means they are 0 along our surface. And of course, they satisfy this condition, omega ij is equal to minus omega ji, omega ii is 0, okay? And if you differentiate d theta I, you obtain this formula, so this is these Cartan equations, yes, and omega ij, you obtain this. And then we have also such formula, we can define the Gaussian curvature using these forms, and the normal curvature they are given in this way. If you differentiate d omega 1, 2, you obtain minus Gaussian curvature theta 1 wedge theta 2. And if you differentiate omega 3, 4, you obtain minus the normal curvature theta 1 wedge theta 2. Okay. Sorry, not this way. And if you take the Gauss map, yes, and you differentiate it, you obtain this formula. So the Gauss map is immersion at the point Q if and only if the dimension of this space, yes, is 2, spanned by this. You should put, sorry, it should be spanned by this, I forgot span, by this one forms. They are one forms on a surface, yes, on a two-dimensional manifold. So it's easy to see that generically the Gauss map is immersion. Why? Because you have the matrix 2 by 4. Yes, because you have you have one forms on two-dimensional manifolds, and there are 4 of them. So we need 3 conditions, yes, that the matrix drop the rank by 1, at least 3. That you take determinant of this and this, this and this, and this and this. For example, if this is not 0, yeah. Okay, so this is precondition. So generically, the Gauss map is immersion. Yes, Little, in fact, proved it in 1969. This condition is equivalent that the Gaussian curvature is 0 at Q, and the delta at Q, the resultant Q is equal to 0 of the second fundamental form. Okay. Oh, sorry. So this is what I already said. For a generic immersion, yes, the Gauss map of a surface in R4 is an immersion. Yes, and therefore it was not very interesting from the point of singularity theory. But now we know that it has 2 components. So we can study the singularities of the components of the Gauss map. Okay, but first I will use this formula that I use as a definition of the Gaussian curvature and the normal curvature to obtain such formula. If you add them, yes, if you add them and take the minus, yes, so we obtained the wedge product of 2 such one forms. If you subtract one from the other, if you subtract from this one, you obtain wedge product of 2 one forms. So what we have? We have that the Gaussian curvature plus the normal curvature is equal to 0 if and only if these 2 one forms are linearly dependent, and Gaussian curvature minus normal curvature is 0 if these 2 one forms are linearly dependent. Why I did it? Let's look for G1 and G2. This is the two components of the Gauss map. They are given by the formula 1 square root of x1 and 1 over square root of y2. But if you differentiate them, you obtain exactly here the same one forms that you have previously. So the kernel of dg1 is equal to the solution of the Paphian systems, yes, the vectors which vanish on these two one forms. And the kernel of G2 is just the vectors which vanish on these two one forms. So this is the Paphian 2, we have two Paphian systems. Okay, so what we get from this? It was proved by Blaschke in 1949, Weiner repeated in 1948, and Hosserman in 1985, that the Jacobian of G1 is just 1/2 of the Gaussian curvature plus normal curvature, and the Jacobian of G2 is 1/2 of the Gaussian curvature minus normal curvature. Yes, Jacobian, the definition, I recall the definition of Jacobian here. So what is the Jacobian? You just take on SI, you have the area form, and you take the pullback by GI of this area form, the standard of SI. SI is the sphere of the radius 1 over square root of 2. Yes, and when you obtain the what? You have the area form on your surface, yes, times the Jacobian of GI. This is the definition. If I go back, okay, look at this formula. If you look for from this formula, immediately obtain this theorem, because dg1 is just this. Yes, yes. So the area form, the pullback of the area form is the wage product of this, and the same for the G2. So this theorem is just follow from these formulas, from these two formulas. Okay. Okay. So now we wanted to study, since the Gauss map does not have generically singularities because it's immersion, but the GI are the maps from a surface to a sphere, two-dimensional sphere. So they can have singularities. Generically, such a map from two-dimensional manifold to two-dimensional manifold have fold and a cusp. And this is the same for GI. And what are geometric conditions in terms of the invariance of the surface? Yes, geometric invariance of the surface. What are generic properties of GI? So the generic properties of GI is the following. The first one, the singular set, yes, of GI is the set when the Gaussian curvature minus, I put it just for all GI because it was plus minus. So if you put I here, this works for GI. Okay. So this singular set, which is Gaussian curvature plus minus normal curvature equal to 0, yes, must be smooth curve. And this is just this condition that you take the differential of this, and this differential on this curve does not vanish. And the kernel of GI is given by these formulas, yes. And the kernels, it transverse to this curve when we have a fold singularity, except a finite number of points when we have cusp singularities, and where it is one tangent, not two tangent. So this is our generic properties, and we have one more, and this the third one. If you take any point, yes, such that the point is singular, yes, of GI, the singular point of GI, P is singular and Q is singular, and this map to the same point, GI, P and Q, yes. So they intersect in a fold, not in a cusp. Yes, this means that the kernel is transverse to the singular set and P and Q. And also, if you look at the image, in the image, the set of singular values intersect at the point transversally, and there are no triple such points. And what we are able to prove using the local description of the Gauss map, yes, you can describe locally any surface in such a way that is a graph of a map, yes, of a map from R2 to R2, yes. The map is AB, and this is just, we are given parameterization using this. And if X is described in this way, this immersion, then G1 is given by this formula and G2 is given by this formula. This R and P are given by these formulas, and H is given by these formulas. What is A10? Where A10 is a differential of partial differential of A with respect of U. And B01 is partial differential of B with respect of V, and the same for the others. Okay, so in fact this G1 and G2 looks quite complicated, and it makes the calculation rather complicated, but in fact we can prove that the properties 1, 3 are generic, and if M satisfies 1, 3, then GI is stable, which I already explained, because the singularities are fault and caps, and you have only transverse intersections in the, and no triple points, okay, in the fault points. So the way the proof is the following. You just have to describe, to prove that this map, yes, if you have X given as a graph of F is AB, then the map that maps the 4jet of F to the 3jet of GI is a submersion. It's a quite complicated calculationally, so we use Mathematica to calculate this, but at the end we are able to prove it. Okay, but when I talk about this in San Carlos on the last workshop, so experts from using a singularity theory to differential geometry like Sidinia, like Farid, ask me questions, because usually if you have some geometric invariant, you can describe it by the contact with some objects like a plane, like a surface. So how we can describe these singularities of this Gauss map, of these components of Gauss map using the contact? I didn't know the answer, but on my talk was also, I think the question was, because we have, you know, these components of the Gauss maps. Maybe I go back. So, oh no, not, when I'm going back, I'm going forward. Sorry, I'm going back. Okay. Oh, look at this. So the singular set of G1 is the set when the Gaussian curvature plus normal curvature is equal to 0. And the singular set of G2 is equal to 0 when the Gaussian curvature is equal to normal curvature. Except some very simple example like a plane, I didn't know the other surfaces for which G1 is constant. So it's singular at every point, and G2 is constant, because usually if you take, for example, the Gauss map of a surface in R3, so you can describe the singularities using the contact of submanifold with planes. But this is not the case here. The planes are okay, but they are not all. And in fact, during my talk, there was present Rémi Langevin, and he could answer my question about it. What are the submanifold surfaces for which the GI are constant, are singular at every point? And the answer, in fact, it appears in somehow hidden in the paper of Hoffmann-Ossermann in 1985. If M is connected, and then for every point P in M is a surface, of course, oriented surface in R4, yes, immersed in R4. GI at P is constant if and only if there exists an orthogonal complex structure J on R4, preserving orientation of R4, for I equal to 1 for G1 and reserving orientation of R4 for I equal to 2, such that M is a holomorphic curve on C2 with this complex structure. So what is the orthogonal complex structure? The orthogonal complex structure on R4 is such a structure for which this matrix J is orthogonal matrix. Yes, such a complex structure constant. Such a complex structure are constant, and using this fact that they are constant, which is not so difficult because we know how the orthogonal map can look like. Yes, so using this fact, it is easy to prove that this must be a holomorphic curve with respect to this complex structure J. Okay, so now the problem was that we have to study the contact with our surface with this holomorphic curves. Yes, so how we will do it? So we also we can locally describe as a graph of a map, yes, AB from R2 to R2. We assume also that all the partial derivatives at 0 are 0 to put it horizontally. Yes, we use a Monge form, and we study the contact of M with the holomorphic curves. This is, in this case, for G1, it is just the standard holomorphic structure which from R4 makes C2. Yes, and the holomorphic curve is given by this formula. It's a graph of a holomorphic function from C to C. Yes, and Z is X plus IY. Yes, okay. So then we have the following. We have the contact map in this way. H of XY is just A of XY minus the real part of this holomorphic curve, yeah, of this holomorphic function, in fact, phi. Bxy minus the imaginary part of this holomorphic function. Yes, and using this, first of all, where I defined some points. We call a point that the point is G1 elliptic if the Gaussian curvature plus the normal curvature at this point are positive. And the point is G1 hyperbolic if the Gaussian curvature plus the normal curvature at this point is negative. I will show all the result only for G1, but the same analogous result can be obtained for G2. Okay. Sorry, not this way. Okay, so we can obtain the following result. If H is the contact map germ of M and holomorphic curve with the highest contact in SZ at P, then the point P is G1 elliptic if and only if H is a contact equivalent to a map germ at 0 with the 2Z of the form x1 square plus x2 square 0. I will write it quickly. The second Z of H is equivalent to x1 square plus x2 square 0. So you see it. This is just the elliptic quadratic form. Yes. So therefore we call it G1 elliptic. And P is G1 hyperbolic. Yes. If H is contact equivalent to a map gem at 0 with a 2Z of this form, x1, x2, comma 0. Yes. And P is a corank 1 singular point of G1 if and only if the H is contact equivalent to a map germ at 0 with the second jet of the form x1 square comma 0, so like parabolic, yes? And P is a fault point of G1 if and only if, in fact, now we use this fed jet, H is contact equivalent to a map germ at 0 with the free jet of the form x1 square plus x2 cube, comma 0. The second component is 0. And P is a cusp point of G1 if and only if, yes, the fourth jet, yes, F is contact equivalent to a map germ at 0 with the fourth jet of this form x1 square plus minus x2 to the power 4. These plus minus are responsible for the positive and negative cusp, yes, because if you have the oriented manifolds, you can say that you can distinguish the positive cusps and negative cusps. In our case, both manifolds are oriented. Our surface is oriented, and the surface is and the sphere is oriented. Okay, so we can say about positive and negative cusps. And P is a current 2 singular point of G1 if the second jet of H is equivalent to the map germ with the second jet 0, 0. Okay, so this is the result. It's, in fact, we used a lot Mathematica to obtain because it is very, very calculational result. I think it was maybe the case why these singularities of the components of the Gauss maps were never studied before, because this is huge calculational problem. We have to use Mathematica, and even in some tricky way, but we are not very satisfied with the result that we can describe using only this huge calculation, because this calculation sometimes takes something like 100 pages to obtain the last result. Yes, 100 pages of Mathematica if you print it. Yes, but the result is something that we expected, and it took us a lot of time, in fact, to calculate this, because Mathematica stopped if you don't use it in a smart way. Yes, you have to use it in a smart way. If you put just it is exactly when it goes to get this equivalence, it will stop after 1 hour and say that it is not possible to get these results. Okay, but so we also want to get some explanation, geometrical explanation, and at the level of this elliptic, hyperbolic, and this result, current 1 singular point, that we can get it. Some explanation which are geometrically, and this result, it's not so difficult, in fact, calculationally. You can calculate by hands, yes, this result up to this point, but we also get some explanation. Okay, and now I will present it. Okay, so the second fundamental form of M, yes, if you have a surface in R4, it has such a way, yes, so you can consider it as the element of the tensor product of the quadratic forms on M, yes, and the section on the normal bundle, yes, and the section of the normal bundle. In fact, it has this following form when omega ij are the connection form, E1 and theta, EI and theta I are just the EI, E1, E2, E3, E4 is the Darboux frame, and theta I are the dual one, yes. So this is the form of the second fundamental form. Okay, but when if you study the second jet and you assume that the tangent planes, yes, the tangent planes at the point of your surface and the holomorphic curve C are the same, so you just, if you study the contact, you just study the difference of the second fundamental form of your surface, and the second fundamental form of a holomorphic curve. And the second fundamental form of the holomorphic curve, since gi, g1 is constant on it, it has a simple form. You have only c1, c2, the two coefficients, yes? These two coefficients, yes, which are responsible, of course, for c1 is just omega 1 free for this curve, yes, at E1, yes, and so on, and so on. And C2 is omega 1 4 on E1. But since they are related, yes, then you have only these two coefficients. And so this is the second fundamental form for the holomorphic curve. Okay, if you subtract one from the other, you obtain such an element of this space, of this quadratic forms on M, tensor product with the section of the normal bundle to M. Okay, so we describe in this way. Q3, this depends on C1, C2, and Q4, C1, C2. And we want to choose such a holomorphic curves among which are tangent at this point to our surface, that they have the higher order of contact. Okay, and what it means geometrically. So we have this quadratic form, the element quadratic form Q3 times E3 and quadratic forms Q4 times E4. And we want to find such C1, C2 that this quadratic form could be written as a tensor product of quadratic form and a section of this. Yes, so it's a such simple element of this. Yes, and what it means, this exactly means that these two forms, Q3 quadratic forms and Q4, are linearly dependent. Yes, and then there is only one solution, one C1, C2, that satisfies this condition that they are linearly dependent. Yes, yes, and then, so then we can describe it. And this form, this, if our point is G1 elliptic, so this quadratic form is elliptic. If our point P is G1 hyperbolic, this quadratic form is hyperbolic. And of course, it could be also parabolic when G1 is singular. And then we can choose a Darboux frame in a such way that we choose that along our singular set, this first vector, E1, is in the kernel of G1. And E3 is just the mean curvature vector field. Yes, because mean curvature vector field, I should put divided by the norm of H, because H does not have to have a norm 1. I should put the norm of H. Oh, sorry. Yes, and then we have this normal form, and for the parabolic case. So you see, this form is really parabolic, and we get it something for free. Someone for free without this calculation. So we are looking now for the third and fourth jet, but this third order invariants and fourth order invariant are not so easy to get. So we get them from calculation, but we don't have the nice invariant language to describe them. So I'm sorry, can you hear me? Do I have some, how much time do I have now?
Phillips, keep going, don't mind.
Okay, because I don't know. Okay, so I will say also about some Gauss-Bonnet time formulas that we can obtain. And when this is the last part of my talk. Okay, so from the Gauss-Bonnet formulas for fronts, yes, and for coherent tangent bundle, we can obtain some formulas. In fact, if you have a map from a surface to a surface, then this map is a from this map you can obtain coherent tangent bundles in sense of Kentaro-Saji, Umehara-Yamada. And then we can prove using their result the following theorem, that if M is an oriented closed surface and we have an immersion which is generic, in this sense we need only the properties 1 and 2. The properties 1 and 2 guarantee that the singularities of GI are only a fold and cusp, and this is enough. Then we have such formula that 2 pi times the Euler characteristic of M is equal to the integral over the surface, dA is just the area from the surface, of the absolute value of the Gaussian curvature plus minus normal curvature, plus 2 times, and here we have the integral of the Gaussian curvature with respect to the arc length parameter, yes, and we integrate this Gaussian curvature on the singular set. Of course, we have the one formula for the plus and the other formula for the minus. So such formula, I think it is not known. It was not known before. So we have such formula. Okay. And the second one, the same assumption. So we have M is oriented closed surface, and the immersion satisfied properties 1 and 2. Then we have such formulas. Here is 1 over pi. So this is the total Gaussian curvature of M. Yes. And here we have the sum from I to 1. And here we have what? We have the Euler characteristic of Mi plus. Mi plus is just this set. Yes. So this is the set which are, we can say, of now if we use this hyperbolic points, G1 hyperbolic and G1 elliptic and G2 hyperbolic and G2 hyperbolic and G2 elliptic. So this is just the sets. Yes, exactly these sets. So we subtract, and here what we have? Here we have the number of positive cusp minus the number of negative cusp of GI. These positive and negative cusps are can be defined if you have orientation of your surface. Yes, because if you have orientation of your surface, if you look at the cusp, if you look at the set of critical values, you have something inside of cusp or outside the cusp, and you look at the set and you look at the set which preserve on inverse your outside of cusp, not in the inner part of cusp, but outside of cusp. You can look if the orientation is preserving or reserving. If it's preserving, its cusp is positive. If it is reserving, the cusp is negative. So in this way, you can distinguish the positive cusp and negative cusp. Okay. And the second formula is similar, only here you see this -1 to the A minus 1. And here you have not the total Gaussian curvature, but the total normal curvature. Okay. So then we obtain these two formulas, which they can be, not this way, which they can be simplified if you have embedding. Yes, if you have embedding, not immersion, which satisfies the formula 1 and 2, then you know that if you have embedding, this is the Euler characteristic. Yes, because for the embedding. Okay, then also, okay, then you have this, that the Gaussian, the Euler characteristic of M is equal to the Euler characteristic of Mi plus 1/2 of the difference of the number of positive cusps minus negative cusp, and the Euler characteristic of Mi minus is equals to 1/2 of the difference of the Gaussian curvature minus of the positive cusp of GI minus negative cusp of GI for I equal to 1, 2. Okay, and that's all. Thank you very much for your attention.